thanks to all the volunteers that works every day very hard for the organization of this event. This is the team working in Oslo. As you see, is pretty big, and thanks to all of them, we could organize these 3 days of science. But not only the volunteers, of course. If we are here tonight, is obviously thanks to our speakers. We are very so we couldn't do most of what we do without our sponsors. This year, we are supported by Simula. Simula also supported the last 2 editions. So the first 2, let's say, editions, and also this Pint 22. NMBU is our sponsor, one of our sponsors also for this year, and we are also supported by Comites. The very last thing before leaving the floor to one of our sponsors is, well, we of course work a lot, but we also need your feedback to improve, to try to create something better every year, every time, for every single event that we try to organize. So please send us your feedbacks. And if anyone wants to join the team is always ready to have new volunteers. There's always something to do. So even if we are a lot of people, but we always need help. So please, if anyone is interested in science communication, we are very happy to have you in the Oslo team. Now, I would invite here Maria, which is also one of our speakers, but will present now yes, very quickly. We'll present now NMBU. Maria or Chairman? Who is going to present NMBU? Sorry. Okay, so just a quick switch of the microphone. And yes, please, Torbjörn.
So what's the...
Yes.
Yes. We don't actually know anything about this presentation.
Just switch on the
You have notes?
well,
Okay.
just a few, yeah.
Like
When
this.
it's blue.
Yeah. Okay. So, okay. 2 minutes. Okay. I'm very excited about this because the thing is that I thought that Maria was going to make this presentation of NMBU, and she thought I was going to do it. And then she got a presentation from the central administration of NMBU. And I had no idea what's on it. Okay.
Okay, we will manage. Both of us, we are from NMBU, so we can.
So why don't you?
No, because we have no idea.
Okay.
Yeah, it's sorry, we just.
Okay, it says something about that NMBU are going to make something for the life. Is this working? No? Oh, it's 48 slides in 5 minutes.
Oh,
Shall we try again? Yes.
yes.
Okay, yes. Okay. So I think that the NBU is by the this goals. That's everything we have to do.
Yeah.
Yeah.
Yeah,
All we
the
have to.
idea is the strategy actually that we have to follow. Like NMBU's aim is to follow the sustainability goals.
Yeah. So whatever we study, we have to say that okay, I'm in this or this and this one, and then they will say, okay, we'll give you money. It's a very good small university, sited 30 kilometers south of Oslo. It's in the agriculture environment, so it's and we are doing a lot. Should I just say that it's the best university in Norway, and just go through the slides? And since it's in Norwegian, none of you will understand it anyway. So, and it's also old because we have a new headmaster, or rector, what do you call it? It's Kurt Rice from Oslo Met that have joined us instead of him. So, but you can study a lot of types of science. We doesn't only have agriculture, but we have also robotics. This is a robot that's called Torvald. It's instead of have these huge tractors on the field, you can have this remote light thing that's just going and doesn't harm the soil that much. So it's and you don't need manpower. And then we have the veterinarian that they have built the huge Poodle Palace. They used 6 or 7 billion kroners to build this huge house for the vets. And but it's a lot of things that are invented, like the Jarlsberg. So I think it's a very nice and small university that's you all should go to and visit. Okay, is that enough? I think it's a few more slides, but you can. Thank you.
It's perfect.
Oh, how you can add?
Thank you.
Etty.
Thank you. So I will leave the floor now to Agnieszka for the quiz.
Oh.
Yes, it's your time.
Yeah, because I think there's no microphone. I cannot.
This is active.
Hello, 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 hello. Okay, everybody. So right now, my name is Agnieszka. As you know, I work at an MBU. And today I will be the chair for the quiz. So before we start all the presentations about today's nights, we would like to test your knowledge. And then our speakers, they will answer the questions for you. So I don't know if you know Mentimeter. So you have to take your phones in your hands, go to menti.com and put the code that you can see there, 69907957. Do we have something special for the winner?
Yes.
Yes, we have something special for the winner. Oh. Oh, magic. Are you in, guys? Yeah. Okie doke. We done? Set? Okay, so let's see. Question number 1. Yeah, if you answer fast, then more points. Which country in the world eats most meat per person? Brazil, USA, or Argentina? Don't say it out loud, come on. I mean, I don't know the answer, but. Okay, USA, and that is correct. Let's see who was the first. Oh my god. Ta-da-da! Okay. We have Ty, Brand the Broken, and Johnny. Okay. Let's see the next one. Question number 2. Yes. How much electricity is coming from solar energy worldwide? 0.2, 2.8, or 8.3%? Wow. Okay. That's interesting. I didn't know also. Maren, nice. Okay, so we have changed. Okay, next one. Let's see how it goes. One country alone is estimated to eat more than a quarter of all meat and half of all pork in the world every year. Wow. Which country? China, USA, Japan. Oh. Yeah, I would vote the same. China. Yeah. And okay. Nothing has changed at the top. Question number 4. What was the first modern solar cell? When was the first modern solar cell made? Yes. 54, 1978, or 95? 1954. Okay. Wow. That is interesting knowledge then. And let's see. Oh, I think we'll have to change. Okay. So everything is unpredictable. Yeah, because it's changing. Like usually, like there's a lead, right? Which country drinks most beer per person? Oh my god. Russia, Germany, or Czech Republic? Wow, I have. Oh my god. Yeah, for sure. Come on. Czech Republic, and I would say the same. They have one of the best. Uh-huh. Ta-ta-ta-ta-ta-ta-ta. Okay. Fafnir the dragon is first now. Question number 6. What do you see in this picture? Worldwide meat consumption, solar cells in Norway, electric cars in China. Oh, that's a good answer also. 3, 2, 1. Oh, okay. Solar cells in Norway. Whoa. Okay. Fafnir, it's safe. Next. 7. Everything can change, as we can see. Where is the world's largest power plant located? California, Tunisia, Mexico. Hmm. 1 and 0. Time's up. And it's in California. And I would say this is the same. I mean, I would answer the same. Anyway, this is the correct answer. Yeah. Okay. Whoa. A new winner. Let's see if it will stay that way. Which country has the highest proportion of electric vehicles in its car fleet? China, Japan, Norway. Yeah, of course, Norway. It's like everywhere. Okay, Matt stays. Last question. What percentage of the sun's energy that hits a solar cell is on average converted into electricity? 20, 40, or 60%? Whoa, a little bit depressing. And the last, I know, before the last question, let's see. Okay, who was the fastest? Okay. Okay, now everything will turn out like the last question. How many motorbikes are there per person in Hanoi? And oh my God. Yeah, basically in China. Oh my God. Wow. Okay. And ta-da-da-dang. Ta-da-da-dang. Ta-da! Congrats! Yeah, so Matt, you have a special, yeah.
I mean, I wouldn't be
Yeah, so thank you so much. And now, Matt, that's the prize for you. You are selected to be a chair.
Yeah, we should pass the prize on to someone who's not an organizer.
But this is the one. Okay.
Yeah, and switch it on.
Hello. Okay. Thank you. All right, getting everything started. How is everyone doing tonight? I see a lot of good beers, a lot of good drinks, some smiles. I like that people are actually sitting towards the front. This isn't middle school. I'm really excited about today's speakers. Today's theme is sustainability and how we can be, more sustainable and curb our consumption and leave a better world to the future. So I'm going to start. Our first speaker is Arve. He's a researcher at the Center of Development and the Environment and Include Research Center for Socially Inclusive Energy Transition. Has a PhD in human geography, but works interdisciplinary, which I always love to see. His main focus is on consumption and sustainability, and he leads the center's research group on sustainable consumption and energy equity. Arve's work is split between consumption patterns in Norway and among emerging middle class in Asia. Welcome. Can we a nice warm welcome for Arve.
Thank you very much. Oh, both. Oh, yeah. I get it. All right. Thank you very much. I'll time myself. Guilty of a few of those questions that you just had to try to answer. Much of my research time has been spent on one of those motorbikes in Hanoi. But yeah, sustainable consumption. So there are so many ways I could approach this issue, obviously. What I'll try to do is to sort of give some snapshots of my own research and some of the main issues, the way I see it, and I think many would agree with me. I'll be very fast, so if you have questions, then please ask them, and also feel very free to contact me afterwards if you have any questions about any of this. All right. Well, quite obviously, consumption matters. We tend to focus a lot on production in sustainability issues globally. Consumption is related, and household consumption is related to very large parts of the world's greenhouse gas emissions, and to land use and material use and water use. So you can see on these figures. The main categories are, I think, unsurprisingly, mobility, housing, heating and cooling of houses, and food. And I'll focus. I'll talk a bit about shelter and a bit about mobility, and I'll focus mainly on food today. The result, of course, of continuous increase in consumption globally is continuous increase in resource use and emissions. Dealing with consumption has sort of always been mentioned when we deal with sustainability, but very rarely been dealt with. It's getting a lot more attention now, actually, some 30, 40 years into, 50 years even into our sustainability approaches globally. And here just illustrated by a recent piece in a leading energy journal and a scholarly tweet about the sixth IPCC assessment report, which for the first time included consumption and sort of the social dimensions of sustainability. So it's getting a lot more attention. So consumption obviously matters, but we should remember also that just because household consumption contributes to more than 70% of global emissions doesn't mean that is all because of consumers, right? And it certainly does not mean that we should focus all attention on consumers. And one of my sort of starting points and main messages today is related to just that. So we need to focus on consumption, and we need to focus more on consumption. And it's consumers that try to live sustainably obviously matter, but focusing on individual consumers, which we tend to end up with when consumption enters the picture, is the wrong way to go. And I'll try to explain why. And this is about as certain as I get, so I'm quite confident. And this should, again, be obvious, but if you start to pay attention to this, you will see that that's what we end up with. Over and over again, when consumption enters the picture, we end up with sort of us, that we should be able, that we should somehow change our attitudes or values and behavior. All right, so this is and I'll explain more what I mean. This is the context. By far, the global north, so-called, consumes most per person, but the line does not go clearly between the global north and the south. It goes between social classes across borders. And the biggest change that we've seen in recent decades is a shift of global consumer markets to the south, so-called, but mainly to the east. So first we had global production, the famous global shift where, as we say, the gravity of the world economy moved eastwards, and consumer markets are doing the same. And this is driven by a very rapid expansion in the so-called global middle classes or global consumer classes. It's expected to, it's about 3.2 billion strong, and is growing very rapidly, then mainly in Asia. Some 92% of the expansion is taking place in Asia. This does not mean necessarily a lot of rich people. The vast majority of these middle classes are relatively poor, but they are consumers. They have purchasing power to some extent. So examples, you say? Well, yes. Let's focus on, for a little bit, on the two biggest success stories in recent decades in terms of development. And the two biggest success stories in global capitalism are two communist regimes, China and Vietnam. By far, if you look at any kind of statistics, the increasing living standards and the economic growth in these two countries outcompetes anywhere else. And what does that mean in terms of consumption? Well, some of it you saw already in the quiz. There's one motorbike per person on average in Ho Chi Minh City and Hanoi in Vietnam. There's not in China because they're banned in all cities, more or less. China has seen an expansion in cars, and this is, but not to the extent that we've seen here, for example. So this graph, I don't know if you can see it, but it shows the change in consumption per household of a range of durable goods from the early 2000s and then until 2016, based on official statistics in China and Vietnam. And I don't have time to go into detail, but basically a massive expansion in a range of consumer goods. I already mentioned the motorbikes, which went from almost none in the 1980s to 60 million today. And cars have seen a very fast expansion in China, but not, they're very, very, very far from the level of cars per capita that we have here, partly because there are very strict restrictions on car ownership in many Chinese cities. But also telephones, massive expansion here, refrigerators, TVs, computers, air conditioners, washing machines, and basically anything. And moving around, as I said, is one of the core issues of sustainability. And oh yeah, I also included just, anything that China gets into, they become the biggest very fast, right? So they're about to become the world's biggest film market. They are the biggest retail market in the world. They're about to become the world's biggest fashion market, and they're the biggest luxury market, and they're the biggest electric vehicle market, and they're the biggest of everything, basically. Because there's a lot of people as well, right? And in terms of mobility, my main point will draw on my colleague Desmond McNeil, who has a long history of doing research on transport in developing countries. And he asked me once, when I was doing research in Hanoi in Vietnam, he asked me, why are people sort of starting to change towards cars from motorbikes. Motorbikes actually work in terms of mobility. And well, I told him, the car represents the future. And he said this, that I keep on using. We've seen the future, it doesn't work. And this is a picture of the macet, as it's called, the traffic jams in Jakarta in Indonesia, where it's quite common to spend 2 hours every day to work. As I said, in Vietnam, the motorbikes have dominated the transport scene, but also their cars have been gradually not taken over because people keep their motorbikes, but they've been more dominant. And cars take something like 7 times the space of a motorbike in streets. So it's a development that has huge implications. But of course, mobility is not only land transport; it's also flights, which tends to get a lot of attention now. This is an image today, a screenshot this morning at 11:35, and right then, at that moment. There are 100,000 flights taking off and landing in the world every day. And if you want a reason to worry, so flights, air mobility only contributes a quite small share to global emissions. But if you want a reason to worry, something like 11% of the world's population has ever taken a flight. And only 4% has ever been on an international flight. So there is room for expansion, to put it that way. And it's by far dominated by frequent flyers. This is something that I've also looked into. And done a little bit of research on. It's a very interesting topic because our means of transportation are not there usually in order to consume them in themselves, right? They are there for a reason. They give us opportunities to move around, and flights have this extreme ability to expand our social practices. And I think the room here today is an example of it, that we have the possibility of meeting. So I said that we've seen the future and it doesn't work. Of course, there's electrification of car fleets around the world, and that could have an impact. The only country that has been able to actually really electrify it to a significant extent is right here in Norway. China is banning fossil fuel cars, so there will be something will happen there. But they may drive electric cars fueled by coal, which then it sort of it moves the pollution around rather than or displaces it rather than necessarily avoiding it. And there are of course a lot of problems with electric vehicles as well. But I think we need to keep several thoughts in our heads at the same time. We obviously need technological development when it comes to mobility, but we also have to think beyond car-dominated cities, for example. We have to think beyond, flight to dominance. We're in a country where flying is dominating long distance transport. So both flights and cars are here to stay for sure, but we need to work on the alternatives and make it convenient not to fly and not to drive. All right, so over to my main focus of today, which is food. And the main issue within food and sustainability is obviously meat. There has been, again, this massive expansion in consumption around the world. According to UN FAO, Food and Agricultural Organization numbers, in 1961, the average human being ate 23 kilos of meat a year. In 2019, it was 43 kilos a year. And in the same period, the global population doubled. So that means there was a quite extreme expansion in meat consumption. Again, the affluent world, the global north, consumes much more on average than other parts of the world, but almost all of the increase takes place in middle-income countries and to some extent lower-income countries. In 2020, I'm going to give you some numbers of slaughters of animals here. So in 2020, 26.5 million buffaloes were slaughtered, almost 3 million camels, 5 million horses, 293 million cattle, 500 million goats, 600 million sheep, 617 million turkeys, 640 million rabbits, 1.5 billion pigs, 3 billion ducks, and 71 billion chickens. And that 71 billion chickens is an example of what we call poultrification of meat consumption globally. So an extreme increase in chicken consumption. And in 1961, the number was 5 billion. So, you know, that's quite an increase from 5 to 71 billion. You know, there are many reasons for that. One is perhaps that chicken is the perfect industrial meat. It's very easy to produce a lot of it. Livestock contributes to then somewhere between 10 and 18% of total greenhouse gases. Uses 70% of all agricultural land and a very large amount of fresh water, up to 1/3. Unevenly distributed, again, as I said, the darker the color, the more meat per person, basically, on that map to the right. I don't know if you can see this, but it's unevenly distributed across regions, of course. So some regions have very high levels of meat consumption, such as Latin America and, well, the Americas in general, and Europe. And Australia is also among the highest. Actually, the highest per person is Hong Kong, but it's not a country, so it was not in the quiz. It's also an extraordinary inefficient way to feed the world. So that's another problem with meat consumption. Okay, and I've studied Asia. Again, in meat, we call it meatification, the meatification of diets, when meat moves towards the center of human diets. Unevenly distributed, as I said, for example, in rich countries. So yeah, in general, meat consumption increases with income. So the richer we get, the more we eat. But it's not a perfect relationship at all. So for example, the US eats a lot more meat per person than Norway. And Denmark eats a lot more meat per person than Norway. And we can look at Asian countries. And this shows the graph per person, kilos per person. And to take some example, well, two examples, Vietnam and India, they have seen similar developments, similar rapid economic development. They are at almost exact same level of income per capita. But Vietnam has seen an explosion in meat consumption. And I can't find it now because it's behind there, but it's one of these going fast up here. And India at the bottom has not seen an increase at all. There are many reasons for that, of course. And some of these reasons is why consumption is interesting to study, of course. So meat consumption increases due to a lot of reasons, and I tried to organize them into supply and demand here. Upscaling and industrialization of agriculture, more meat-intensive food environments, so where we buy our food, basically, more meaty convenience food, and also, you know, meat tastes good. People like it. Nutrition and health concerns. People think, in general, or many parts of the world, that meat is healthy. And then, of course, meat is part of food cultures. And meat consumption increases as part of food practices and changing food practices. And one of the most important single food practice around the world is then eating out more. So there is, we tend to eat more meat when we eat out than when we eat at home. I don't know, this is very simplified, but yeah. But there's this, what we call co-evolution of supply and demand of meat. Now, I wanted to give you a case that we've been working on, and that is Norway. Norway is a nation of meat eaters, although we don't have extremely high levels compared to other countries at the same income level, but we have extremely high levels of meat per person compared to the world average. So we are about 70-something kilos, the world average being 43. Do you eat meat? This is a recent survey that we did. 97% of the Norwegian population eats meat. And this has been a stable number for a long time. And this shows the different types of meat. We don't have time to go into them. But it's been stable for the past decade or so. the meat consumption in the country, even gone down a little bit. And what we've seen, and I'm sure you noticed, is an increase in so-called flexitarianism. So people trying to reduce their meat consumption, but without going vegetarian. So the number of vegetarians is stable and vegans is stable, but the number of flexitarians has increased. And for us, looking into how the challenges that people face when they try to reduce their meat consumption is a very useful way of understanding consumption and what we call the stubbornness of consumption patterns, the difficulties of changing them. Maybe you know, but meat is insanely polarized in Norway. And it's very difficult to have sort of a rational discussion about meat here because there are so many different interests. This is a screenshot from the Center Party, the former Farmers' Party in Norway, and their campaign in 2020, where they put up this and they say, they want a nation of vegans. They want you and me to feel meat shame when we eat meatballs or meat cakes, as they're called here. And I'm going to move a bit faster. So what we see is that we find it very hard to cut back on their meat consumption. And if we sort of track them and make them do diaries, they do even worse than they thought. So meat sneaks into diets in many ways. And we call it scripted, the meat consumption. This is something that we're working at right now. So it's scripted into the material dimensions of our everyday life. So basically, you go to a restaurant and there's meat everywhere. You go to 7-Eleven, there's meat everywhere. But it's also scripted. It's also built into our social relationships. So meat is expected in a lot of settings. And what is interesting to see is that these meat reducers, they often find it harder than vegetarians. So vegetarians, you made the statement, there's no question, and you're not eating meat. But if you go to a social setting as a flexitarian, many say that they feel, they're being too difficult if they ask for something else than meat. So, and we see this clearly from this research that it's really built into social relations, and it's also built into a lot of ideas of care, nutrition, for example. And many meat producers would, and myself included, give a lot more meat to their children than to themselves, for example. It also has to do with food cultures. Of course, it has to do with culinary competences. We see that people just don't know what to cook. And then you have all these, and this is interesting again, all these meat alternatives, right? Meat replacements, such as the Beyond Burger and so on. And people don't like them. And this is some recent research, not by me, but a meat replacer, no thanks. And this is quite interesting because they are very harshly judged, these meat replacers, because they're processed foods. And many we've talked to as well, and other research finds that people don't want this kind of processed food, and they're much harsher when it comes to judging, the meat replacer processed food than the meat processed food. So, for example, in Norway, we eat a lot of sausages, and something like 100 per person a year, actually. And the vegetarian sausage has not really been able to replace that. Okay, time is running out. I'm talking too much. The future of meat is uncertain. China has offered, or the health authorities in China have said they're cutting back on meat consumption, not the rest of the authorities. There's a lot of attention to meat. There's the meat replacers. There's different kinds of alternative proteins, and there's cultured meat and so on. And this field is going to change quite a lot. And it's quite obvious that we have to do something about meat. This is from the news yesterday, a recent report showing that, or claiming that we need to cut meat consumption by 75% in rich countries to stay within the 1.5 degree, I think was the threshold. And we need, obviously, holistic approaches to understand this. So some of the main insights from some decades of consumption research, and I don't know what happened to the image over there, turn around. But some main insights, just to summarize consumption research in general. If we want to change consumption, value action gaps, as they're called, are very common. We believe one thing, we behave in a different way. Consumption is not an individual matter. Consumption is fundamentally social, and that's agreement all across the social scientific consumption field outside of economics. And just as much of it is about fitting in as is standing out. Normalization processes are the strongest drivers of change. Consumption patterns are in different ways embedded in material settings, basically in infrastructures and in so-called systems of provision. The retail, the production, everything that gives us our consumer goods. And consumption patterns are deeply habituated. A lot of it is relatively unconscious. You don't really think about it much. You do it automatically. And this makes it very difficult to change. It makes consumption very complex. And it means that you choose a lot less than what you like to think. And the consequence is that if we want to change consumption patterns, we should be strategic at what kinds of consumption patterns we want to change instead of just saying, change consumption. But we need to look beyond the individual. We need to look beyond attitudes and values and have holistic approaches. And we need both sticks and carrots. If you want to reduce car driving, for example, we can make cars more expensive and driving less convenient. But we need to also provide alternatives. We need to make it more convenient to ride a bicycle, for example, and walk and so on. If you want to reduce meat consumption, then like Norway, we cannot subsidize meat to the extreme extent that we do as well. And we cannot have meat being a meat eater being cheaper than being a vegetarian, which is often the case in Norway today.
There's so much more I could say about this, but I'm open for any questions, more information for those of you who want that. Thank you so much for this.
We'll have you stay up here and answer some questions. But I think that was really nice to talk, especially the point you made about what it takes to actually stop eating meat. You remind when you're talking. I remember a talk from years ago where someone said, the problem with becoming vegan is at some point you need to decide this is my last cheeseburger, and that's a really hard thing to do and say like from now on I'm not doing this. And this idea of flexitarian, I really like, and I think is a really good thing. And as a fairly newcomer to Norway, I've noticed there's a lot of these meat alternatives, like you were talking about. It seems pretty easy. I don't know if that's influenced how Norwegians, why Norwegians are not eating quite as much meat as other similarly developed countries.
The main reason is fish. We eat a lot of fish. Fish is not included in these meat statistics. So that's the main reason. These meat alternatives are very recent, so they're we're yet to understand the kind of implications they will have. But yeah, good question. And I should add that we used to eat a lot of fish. So the young generations today talk a lot more about eating less meat, but they eat more meat than the older generations, which is interesting.
That's interesting. So yeah, we have a little bit of time for some questions. It was a really fascinating talk. I certainly obviously had some questions. Would anyone in the audience like to come up and ask a question? We have about this much length of microphones. You're gonna have to come up, Tibble, and you got to talk into this one too, so the people at home can hear.
Yeah. Hi. Thanks for the talk. Yeah. Now, regarding the change, so you said like we want to eat less meat. People want to eat less meat, and when they want to move away, it's just like raw veggies or like processed food. Do we need to invent a new kind of diet based on veggies, like basically new recipes and everything, or what can we do?
Good question. There have been attempts. And there are, of course, many cookbooks now, etc. I think to some extent, yes. We tend to do what is most convenient, right? And when cooking meat is deeply embedded in our skills and our practices, it's hard to change. And we did a special study during lockdown where we talked to people in lockdown. And one of the things we talked about was food practices and so on. And you know, quite a lot of people said that you know, they've been wanting to try vegetarian food, and during lockdown they finally had time to try. And then, you know, we're curious to see. We're going to talk to them again and see what happened after lockdown. But yeah, I think we need to change and think holistically about it, and provide alternatives, and give people the skills to eat different things. We have a PhD candidate who is doing research on that. And interestingly, both for insects and for cultured meats, there's a very strong sense of what we call the yuck factor. People don't want it. They don't want the cultured meat. They don't want the insects. But it's doable. You know, big parts of the world have been eating insects for a long time. So.
Great, thanks. Does anyone else a little bit farther away would like to ask a question? No? Yeah, I'm gonna have to ask you to come up because I can't reach you from here.
You mentioned fish like en passant. Do you expect it to be a more sustainable alternative, really, or not? Because I never really read much on that sense.
Yeah, fish is a very interesting topic. It's not my expertise, and it's not included in any of these statistics. You know, if you go and you fish with your rod in the ocean and you eat it, it's quite sustainable. But so it could be if you go and hunt animals. If you eat from industrial fishery, perhaps it still is. If you eat farmed fish, then it's a different question again. If you eat farmed salmon that is claiming a lot of fjords in Norway and eating partly soy from the Amazon, then it starts getting complicated. And there's no stronger lobby in Norway than the salmon lobby, so be careful. But it can be more sustainable and it can be more healthy, but not necessarily. It depends. And again, that's one of the things why meat interests me so much, because it's potentially cutting back, not necessarily eliminating meat consumption, but cutting back on meat consumption is a win-win-win situation. Like it's good for our health, it's good for the environment, and it could be revolutionary for animal well-being. So, yeah, and fish, I will have to look more into it. I'm the son of a fisherman, actually.
Great. If there's no other questions, usually someone jumps in at this point. All right. Well, thank you so much. Another round of applause.
Thank you.
Take a quick break. All right, we're going to take a quick 10-minute break. Get yourself another tasty beverage. I think there's some tacos out there too, and we'll be back in just a few minutes. Thanks. a minute here. If everyone wants to get their seats back. Yeah. I think everyone's here. Last chance to run and grab a beverage. I haven't met our next speaker. Is he here? Is that Thorvald? You are? Okay. Okay, good. I wanted to just check our next speaker is actually here. Did you want to do something first? Are we good? Okay. Our next speaker is Torbjörn. He is motivated to think that everyone should contribute to limiting the climate footprint. And this is a small contribution. He has a doctorate in physics. His research has been based on defects in solar cells so the industry can make better solar cells. This research has led to new measurement methods, which in turn reduces wastage in the production of solar cells. And I'm really interested to hear how solar cells work in Norway because, half the Earth's dark. So, Torbjörn, everyone please give a warm welcome.
Yes. Then you have to hold this. Like this. Thank you.
Yes, very, very important part of finance science.
Thank you. I was not actually going to talk about how solar cells works in Norway, but we can do that first. It's okay. It's no problem. We had a master student doing this research on comparing solar cells in Ås, that's 30 kilometers south from here, to German sites, and found out that it's the same. What you get per square meter in Norway compared to Germany. In Germany, it's a little bit more sun, or the angle of the sun is a little bit better, but you don't have a clear sky. You only have some dimming up in some small skies, high up. There's some clouds, but in Norway, when you first have a clear sky, it's clear, and you have snow in the winter, and then you have the albedo, so you get a reflection from the snow, and you get more. And it's colder as well, and the solar cells are better when it's cold. So it's so we get from in the south of Norway, you get the same as in Germany.
And so what about the quantity produced by the solar panel over 1 year? Is it the same in Norway?
It's the same during the whole year. It's the same as in Germany, but we have in the winter time it's a little bit less, of course. But it's but in the summer we had so much more, and so it's no problem. But we are expensive. The thing here is that since we haven't installed so much, it's very expensive to install it because they don't know how to install it. They use many labor hours to install it compared to Germany that just puts it out. So that's more cost in Norway.
I have another question.
Yes, of course, another question.
Yeah, because I understand the solar panels here in the south, but what about going more north?
Going up more north, it's very good. Also up north, it's not that good as here, of course. But we are also trying to put up solar panels on Svalbard, Spitsbergen, because it's sun all day.
Yeah, but what about winter?
Well, in the winter we have to have something else. So it's, but it's no problem. And since also now we have the new panels are bifacial, so they can get sun from both sides. So then it's you get it during the night as well. So yeah. So what I was going to talk about nudging, or actually what scientists do. We only nudge. We just do a little. We are like taking a PhD in something very special, but for the whole world, it's just a little. It's. But when we get together and many are just pushing, then we will get somewhere. And of course, everyone do some research on something extremely difficult. And I'm doing my research lately was on identification of thermal donor-rich Swarovski silicon wafers using hyperspectral photoluminescence imaging of Shapley Hall recombinations. And of course, this is only words I have fun up. It's you think, but it means something. But for us, it's just bullshit. But the thing why I do this is that I want to also be a little part of this to push into the green. But I have it's so much talk about, oh, you have to think about the climate, and there are so many that doesn't believe in climate change, and there are so much, oh, we have to, yeah. But it doesn't matter, because if you look at this thing, it's like it's spheres that represents the yearly use. For here you have the what do you call it? The Earth. Yeah. So the sphere represents the size of how much energy we use per year, and then you have the sun and how much the sun gives. It's 10 now. It's 1,000 times more than we actually need. But if you look at the oil, gas, uranium, they say, oh, it's limited. So if we only use like gas, we only can use it for 11 more years. Then it's finished if you only use gas. And if you only use oil, okay, we can use it for maybe 20 years. Then it's finished. And then you have, oh, we have to go nuclear, but it's only for 10 years. And then you have also thorium that they are talking about, because we in Norway have thorium as well. We can use that to do it. But thorium is 3 times as much as uranium. So, okay, we have it for 30 years. But that doesn't help. I'm 50-something and want to live 50 years more. And then we have to go into something else. And everyone that's doing research, we know that if you're going years when you are studying something to get to the new. So we have to stop researching and go into solar. And we have other that's so like wind, there are also solar, that's the sun is shining and the wind is blowing because of it. And but my research has been just to go direct from solar to electricity, and then you have solar cells. And there's been a lot of research, and this is also like research. We want to show some graphs that no one understands actually, and but it's going up. It started in the 1975 and going up to this year, and you see that all the different types of solar cells are getting better and better. So a lot of research are just nudging. It's trying to we have a breakthrough from here to here. We have like gained point something. Okay, so okay, we can study this or we can do other things. But what actually have done is that okay, the solar cells itself have become better, and also all the things around the mounting, how you produce it, everything is the cost is going down. So for the last 20 years, it's a lot cheaper, extremely a lot cheaper than before. And this is an old, so it's actually a little bit more expensive this year because of the COVID and But anyway, so in 2018, that was like a milestone in the solar cell industry, because then it was the cheapest thing you can install if you want to make electricity. So if you, instead of like coal or nuclear or gas or wind, you can see that the yellow here is the solar cell. So here, a few years ago, it was the cheapest you can actually do, and that in every country in the world. So so that's very good. And this year we have installed, I think a few weeks ago, they said that, oh no, we have installed 1 terawatt peak of solar cells. And but it's only like, was it on the quiz, 2.8% or something? Yeah, but we are getting up. And they said that in 3 years' time, they will be 4 or 5 terawatts. So they will like 5 times more. So then you're getting close to 10%. And it's easy. So maybe we will get there in a decade or two, hopefully. But to get even lower down here on the cost, then I have tried to study something. To set what actually are the solar cells are made of. It's made of mostly, almost 97% or something, are made of crystalline silicon. And silicon is a material that's sand. So it's the second most, what do you call it, grunnstoff element on the surface of Earth. So we have a lot of it. So it's no problem. But in the end of the process, you have like this multicrystalline. You just have melt something, and then you just want it to cool down and then crystallize, and then you can chop this into pieces and make solar cells of it. Or you can have another process that's where you make a monocrystalline. You make this ingot that's can be a few meters long, and then you chop it into pieces. So what you can see, the difference between these two is that you can see the rounded corners on the mono. And last year, the whole industry stopped producing multicrystalline. They are only going into monocrystalline because it's better. It's fewer defects, but it's a little bit more expensive. It's always been a little bit more expensive to produce, because instead of just put it in this box and cool it down, you have to have a huge machinery, and what you do is you have a melt, and you melt this silicon, and then you put a seed, perfect crystal, and then the melt will cool down around it, and you make a huge crystal. Then you pull it out, and you rotate it as well, and then you have this ingot. But of course, it also have defects. To what I'm actually doing to see all these defects, because and if it's good or bad, you can check it by have light. A photon is a piece of light that's going in. Then you can get an electron and push it out, and it will be free. And if you then are able to connect it with 2 cables, one on the back side and one on the front side, and then you can get this electron to make a light bulb. Yeah, so then you have a solar cell. But if you don't connect anything to it, the electron will go back again, fall back again, and recombine, and then it will send out a light, the same light that got in. But if it's something wrong with the crystal, you will have a trap, and then it will send out a signal that's or a light with lower energy, and then it's longer wavelength. So my research have been to see to capture an image of these lights. Because it's good and bad. Okay, you see if you have a trap, that bad. So I use then a hyperspectral photoluminescence imaging tool. That's also a word we just found out. It's but to look at how it actually is, it's you have a laser that's get the electron up, and then they fall down again, and then you have a camera that takes the image, and then you move the camera across the wafer, and then you will get images of this. And then you can see the signal of all these defects. And what's good is the big here, the band-to-band signal. That's what's actually is blue in the top image here. And then we can look at different types of signals and where it is, and then we can understand, this is because of some oxygen, or this is because of iron. Okay, so then we have to go back to the industry and say, you have to be more careful about iron or something else. So that's what the research industry can do. But then the industry has started on this ingots instead that you put up and pull up. And what's bad about this process is that the top, this is like more than 1,000 degrees in the melt, and then it cools down, and the top part will be around 450 degrees too long. So then it becomes some defects in it. And I met this Eleanor Letty from France on a conference, and she said, I'm going to study this thermal donors, but I don't have any instrument to measure it, because now the industry just they know it's the defects are in the top, so they just cut out the top and throw it away, and then they make solar cell for the rest. That's good. But you can, if you cut out too much, you have a lot of waste that you could have made solar cells of, or you cut it too high, so you make a lot of solar cells you have to throw away. So she asked me to maybe we can collaborate and see if we can see any signals from this defect. So we tried, and of course, we found it. We did this first with a very low temperature. We cooled it down to almost 200 degrees below zero. And then we saw this defect, and it's a ring defect, and it was very nice. And it was, wow, perfect. And then we tried to do it in room temperature as well. Oh, and we found it. It was not that clear. It was a very weak signal, but we could see it anyway. And what we do then, of course, we go to different conferences and oh, look what we have done. But we also thought that, this can be used in the industry. So we didn't like try to blow the whole thing, because if that's very, very, very for a scientist to not blow it, so we can't get a patent out of it. So if you just say, this is how it works, then you can't make a patent. So the French people, they were very restricted what we could share with the rest on this different conferences. And but then we got back and did a little bit more research and found out that if you compare to where this signal in room temperature of where in the ingot, the top is the C then, where I had marked it with red the last, so but here is blue, and you can see that it's in the top, and then when you get a little bit lower, it's okay. And of course, the scientists have to do other experiments as well, and we did a lot of other measurements, and then found something right and did some math, and was able to compare this with the thermal donor's density. So it can the concentration of it. So it can so when you get below a threshold value, it's fine. So then we made a patent application, and so we can find out exactly how this threshold value is. So in a production line, you can just, instead of just cut and throw, you can just cut it in pieces and feed it into the production line and measure, and bad, good. Oh, okay. So, but it doesn't hold only with the patent application. You have to sell it, and we got it. So 1.5 months ago, Semilab bought the license to make this tool. So hopefully, this is my little nudge for to save the planet. That's why I also have put it in small. So hopefully it could lead that they can save a lot of material, and that's also the part where it's most expensive in the whole process. So okay, so we got a lot of money. No, we didn't. It's we got a sign-on fee, and then afterwards that you don't get any money actually. so okay, maybe I'll have one beer a year or something for this, but it doesn't matter. I think I have done my small nudge on this. Yeah, thank you.
Thank you so much. I think that is a noble nudge. So thank you for your work. Does anyone out there have any questions? There's a lot of really good information in that talk. Tibble, did you have a? Yeah.
Oh, of course. No, thanks. This was a really nice demonstration of R&D, of application of research to industry. My question was more regarding the. Can you the sustainability of solar panel. You say that you cannot not recycle the solar panel that has been manufactured.
Yeah. The recycle. So the question was recycle or yeah, the waste or the because they are not going to last forever. But many of here in Norway have cabins up in the mountains and have solar cells panels on them, and they are still working after they installed it in the 70s and 80s. So Norway has actually the what do you call it, the country in the world with most installed solar cells in the 70s and 80s. So we were first on Earth with the solar cells. So that's good because we had money for it. It was very expensive. But now things are, they say that what you buy now, it will last 25 to 30 years. But a lot of have been there already for like 10 to 20, 25 years. So they are starting to, you have to replace them because they are breaking, the contacts are bad. It's not that they are not used up because it's nothing you use up, but it's the contacts and the plastic or the all the other materials in the thing that's make it bad. So you have to replace it. But they say that the EU has said that you have to recycle at least 85% of it. I think that's around that number they said a few years ago. So I was in a conference in Lisbon 1.5 weeks ago, and many of the talks there was about how we can recycle it. And because they haven't any good solution yet. But they are, but some of it is like you take off the aluminium, you take off the glass and the plastic, and then you chop the cells itself into small pieces, and then you heat it, and then the gas, the different temperature of the gas you can sort out the different elements. So, but it's very expensive. But I think in a 5 to 10 years they will have a solution for it. But they are a huge many of scientists that's working on it, but they haven't had a solution yet. So
what about the cell that your technique said is bad? Can you recycle it or?
Oh yeah.
Melting it?
What you we throw away?
Yeah.
But the waste they throw away, then it's a little bit hard to use it again, to melt it again and make a new, because you have got too much oxygen in it and other elements as well. So you have to. It's a long process to just recycle it. So it's just like, it's not like you have water and you make an ice cube and it's dripping a little bit of water and then you cool it down again and then you make a new. It's not like that in the solar cells for the silicon. And also when they chop it into, because the ingot is high and it's 0.2 millimeters thick, one solar cell. So you have a lot of, and then you have to saw it, and 30% of the ingot is kerf, that what you call dust afterwards. So it's a lot of waste as well, and that waste it's almost impossible to use again because the elements in the sawing chain is going into the silicon, and it's like. It must be so extremely pure. It has to be, if the iron is more than what's it? 1 billion? Is it like? Do you know, Maria? No. It's like 1 out of 10 in the. Yeah, some billions. If it's 1 iron atom of several billions silicon, then it's not pure enough. So so the ingot is the purest thing man have made. So it's, and the crystal is only one crystal. Everything is in one direction. Everything. So it's cool.
Yeah. Do we have any more questions? We have time for another question or two from the audience. I see some inquiring looks. Yeah.
All right, thank you. Very interesting. I don't have a clue about this stuff, but I do follow some of the debates, you know, from a more social scientific angle. And what I see is raised very often or always by critics of renewable energy are all the rare earth minerals going into. Can you enlighten us a bit more on the other parts of solar cells? Like, are there big sustainability issues here that you haven't touched on today?
Yeah, you have some elements that you have to use that's not that good, and it's limited. But it's okay. It's not the worst. But the thing now is that they want to put a tandem solar cells. That's a new in the industry now, because if you just almost paint on an other layer, then you have a solar cell on top of the original one. That will then it will increase it with 50% more. So instead of like 20, you can get 30% of the solar cell. Now the sun into electricity. And that's mostly perovskite, and it's a lot of extremely bad elements, lead they use, and others. And I had on my what do you call on my defense, PhD defense, you have to have a talk. No, you have to have a lecture first. You try a lecture, yeah. And that was on perovskites, on this extra layer. And my sister was in the audience, and she's a scientist in, her PhD is in on what do you call it? Toxic. Yeah, she works in Mattilsynet, and she was like, "Oh, everything, all the formulas I put on, all this. How on earth are we going to deal with this? Because it's so extremely toxic." But the physicist doesn't know about it. They think it's cool. So, yeah, but it's yeah. But I think they are trying. And they are also trying to put in other elements. That was also a few talks on another conference. I was trying to change with more elements that's norm or more of, so we don't explode. Even that, like they have all the small strings are silver, and you use a quite many percentage of the silver in the world on solar cells. I think they said that around 25% of all silver is on the solar cells. So they have to make it smaller and or find something else. So it's
the cobalt from cobalt.
yeah, and then you have the cobalt. Yeah. So it's a problem. Yeah.
In the quiz, you mentioned that it was 20% of the light is transformed into electricity. I mean, and that was actually the first invention in 1954, right? So what is the percentage today, or the latest technology?
Yeah.
Can we use only solar panel to power Earth, or?
Yeah, we can use it to power the Earth. because we have 10 times, 1,000 times more solar cells, that we need. But the thing is that first it was only they can gain like 10% of the sun. Now it's around 20, but the limit is 29%. Then you can't because you have to get the electron have to be free. Okay, so you have to have light in to get it up and free. And if the light have more power than it needs to get it up, you don't get that. That would be just waste. And if it's lower, it will the sun will just go straight through it. So you only get so you have like a limit, a threshold value you have to have on the light, and it's the full spectrum. So you can only use so 30% of the sun will just go straight through because the wavelength is too long, and then 1/3 will get lost because it's too high energy. So then you have 1/3 again that you can get. So that's the limit. And now we are making solar cells that can get around 25%. And what you can buy now, it's up to 22. But in the laboratory, 25, 26, something like that. But it's very hard to get more than 20 something. But then you can put another on top that takes the shorter wavelengths, the energy you lose. So then you will get, in theory, 44%. But you also have like they make that almost get 50%, but that's extremely expensive. Then you have 6 layers of solar cells stacked on top of each other. But then that's used when you don't have space, and that's out in space on satellites. And there you have this extremely expensive solar cells that takes more than 50% of the light. Because when you are sending a rocket up in space, you have money. So.
I think we had one more question. Yeah? Or did that answer your question?
Something in the start about if we install, we have only somewhat years to go. If we install solar, how many, do you have an estimate on how many years we can use solar?
We can, because it's renewable. The sun will always.
Sorry, the question was based on coal that we only have 10 years.
There was some material that
Yeah.
And then how long do we have for solar?
Yeah, infinite. It's it will never go away. It will always come again. So we have more than we can use, and the sun is shining, so we will.
So the silver is not a problem. There's no problem.
Yeah, because they will have problems. I think if they just don't research anymore and just make it like now, maybe they will get to finding out new methods. They will. I don't think that will be a problem.
Yeah. Is it so there's one more question in the back. Could you come up so we can hear your question? Otherwise, the people at home won't be able to hear it. That's okay. That's why I repeated yours. Both. Okay. This is for here. This is for the people at home.
All right. So I guess when we're using solar power, there's always a constant question about what about energy storage, battery technology, and so on. How far have we come? Because I mean, when you mention we can extract up to 20% of the energy from the sun as light, as electricity. Even if theoretically it's 100%, if the sun only shines for 12 hours of the day, that's still 50% in a day. So how far have we come in terms of the energy storage batteries and I guess other methods as well?
I don't know.
It's always good to be able to say that.
I think it's extremely much research on it because that's the only thing we have left to find out. That's the battery. That's the main problem now, and how to solve that because so it's a lot of thing on how you can store it, not like only in batteries, but in different. You have you split something like not actually like water, like the hydrogen and oxygen in each part, and then you combine it, and then you have electricity. Something like that. You find something that you can use energy to pull apart, and when you go back again, you get some heat, and then you can make electricity again. So that I think that's the solution for the big storage to have. So I know it's a lot of very interesting scientists that works on this. So I think it's but we need a few more decades to sort it out, I think.
Yeah.
And yeah. And Maria is going to talk about something similar.
Yeah.
But so she is like when you talked about you asked about what do you do when they are broken, and she will find out why or which one are broken. So that's also a big industry.
Great. Well, thank you so much. Great, another warm round of applause. Are we taking a break? Take a break. Break. All right, we're going to take another quick 10-minute break. Hydrate yourselves, go grab a snack, and we will be right back with partially introduce Maria. to start making their way back. I think I saw some people still going out. We'll get started in just a minute or so. Make sure you've got your hydration and you're ready to hear some more about solar panels. Not going to be here tomorrow. Everyone, are you all ready for the last talk of the evening? I'm excited for all of it. I always like to hear a presentation and then another presentation that kind of follows in on an aspect of that. It's always also really nice to hear from a graduate student. Having been one, I know how that can be. But it's always great to hear the sort of like current, very current, active in-process research. And our last speaker, Maria, is a PhD student at the Solar Energy Group at the Norwegian University of Life Science in Ås, working to detect defects in solar cell modules based on images. She has a master's degree in environmental physics and renewable energy from the same university. And I'm excited to hear some more about solar panels and how we can make them better. So take it away.
Great. Thank you. Thank you, Point of Science, for having me. Hi, everybody. My name is Maria. I'm a PhD student. And I work in the same research group as Torbjörn. The difference, however, between our research work is that Torbjörn works in the lab while I work out here on the test site of the NMBU, where we have installed several modules, as you can see here. But the physics, the underlying principles that we're using in our research, they're the same. However, working outside poses different challenges, and there are different aspects to be taken into consideration as opposed to working inside in controlled environments. First of all, as Torbjörn mentioned, he works with these little devices, 15 millimeters times 15 millimeters solar cells, while I'm supposed to take images of the whole modules. So PV solar cell module, this is this bigger device, which consists of 60 of solar cells. And also, what you also see here is a group of modules. We have 12 here. And I'm also supposed to not only image one module at a time, but also develop a method to be able to work on a whole group of them. And I will come back at the why that is so. So two important differences when it comes to working in the lab and working here outside. First of all, we don't have any control of the weather. We need to adapt to the weather. Rain, wind. The wind can shake our camera while imaging if it's really strong. I didn't believe that was the case because the camera is on the tripod, so I thought it was stable enough, but I was proven to be wrong. The sun needs to be, ideally, there shouldn't be any clouds, but if there's a little cloud that covers for the sun during the imaging, then the whole image series that we have collected is not usable. And also, these modules, they are in operation. As opposed to looking at small cells in the lab, They don't, usually when we work in the lab, we don't make them produce electricity. We could, but we don't. So that is, let's say, that is one parameter less to take into account. But here, these modules are in production. They're connected to the grid. And that is something that we need to take into consideration. I will come back to why that is a problem, actually. That is a big challenge. So first of all, what am I working with? I'll try to explain what these images are. This is not an image that I have taken. This is an MR image of a human head. And the reason I'm showing it is because I think the images that I'm working with are a good comparison with, or a good way to understand is to look at MR images. MR images, they give us an insight into something that we can't see with our bare eyes. They give us an insight into condition of a human body or a part of a human body. And these are the images that I'm supposed to acquire in the field. Here we have a module which is broken. And we know that it's broken because we know that a colleague of ours smashed it in the storage room. So that is a very valuable object now for me. Hopefully, I mean, as many of these as I can get, it is a good thing. But this is not something that we can see with our bare eyes. We see on the glass that it is smashed, but we cannot see on the solar cell material that it is smashed. And we don't know where the breaks are, where the cells have been broken. So you see here this homogeneous color, yellow, orange. Everywhere where the color is homogeneous, it means that the solar cell is healthy. If you see here, purple, black lines and unhomogeneous color distribution, that means that all of these parts, it means that the cells have been broken. So that is a similarity with MR images. We acquire information about something that we can't see with our eyes. Also compared to MR equipment, which is expensive and it's not something that is used that you see in everyday life very often, apart if you need to go to a doctor. The cameras that we use are also cameras that are expensive and not something that you would order and use on daily basis. However, when it comes to the procedure for MR imaging, as far as I understand, that is an established procedure. You know, when you go to your doctor and you need an MR image, the doctor knows how that needs to be done. We still don't know how to take these images. We are developing a method. There are a few other groups in the world, in Australia, in Germany, Italy, maybe one more that I'm forgetting now. And we all work with developing a method how to acquire these images because they're difficult to acquire. And one more aspect that can be compared to MR images. When you get an MR image, then you expect your doctor to be able to interpret and say what has happened or where the problem is, if a bone is broken and so on. We still are learning to interpret the images that we're acquiring because there are different types of defects that might be on this image that I still don't know they are here, that I still can't recognize because I don't have the knowledge. I haven't seen these defects many times enough so that I can see, okay, this defect, this is how this problem looks on the image. So we're still learning to interpret the images as opposed to MR images, which hopefully a doctor knows how to interpret. So this is that is why the title of my presentation is Fault Detection in PV Modules Based on Images. Or when I started working with the presentation, I thought maybe diagnosing a PV module with images would have been a better word. But that is what I'm working with. So the question is why? Why are we doing this? If it is so difficult to achieve outside in an uncontrollable environment. And if you consider a PV power plant like this one, and you're an operator here, then you would like to know the state of your modules. Obviously, you would want to harvest as much sun as possible, and you wouldn't want your modules to be broken, or whatever can happen with them. And finding the module that it isn't working properly isn't that easy in this vast sea of modules. And you might think, well, isn't there electrical data that one can acquire? These modules produce electricity, so isn't there data that can be sent to a central station somewhere that can be interpreted? There is, but it doesn't necessarily work that way. You would, it depends on whether you have good enough equipment to get data sent remotely to you. Also, when you get data sent to you on your computer, you get data sent for a whole group of images, as I explained, a whole group of modules. As I explained earlier, we have on our test site at NMBU, we have 12 modules connected together. So you get the information for the whole group. You don't get the information on the module level. So if you see that there's something wrong with the group of modules, you still need to go there and start disconnecting, and you don't know which module there's something wrong with. Also, you might be forced to go physically to each and every of these groups, connect your piece of equipment, measure, and then go to the next one, which again is not as efficient as imaging could be. So putting a camera in a drone and flying over a test site, and then getting images of several, not only modules, but several groups of modules, could give you more information about where the defects modules are. And then you might ask, well, aren't there drones in use already? There are. For example, with thermal infrared cameras, you can put a thermal infrared camera in a drone, and here you see a thermal infrared image. Thermal infrared images, they show you temperature distribution across these modules. And here where you have yellow color means that the temperature has increased because something is wrong with the cells, compared to the purple and pink areas here, which are fine. But if you compare these images with this one here, and you see that there's more information to be obtained, more information on the cell level, here, for example, as opposed to here. Here you see the whole cell has increased temperature. You don't know what the problem is. You don't know where exactly is the defect and what it is. So thermal infrared images, they can be useful and efficient to collect information, but they also don't tell us everything we'd like. So we believe that developing this method would be very useful for surveillance and monitoring of big PV power plants. So how does this work? I will explain shortly why this is difficult to achieve, and why the research on this started only 5 to 6 years ago. I mean, the imaging of solar cells and modules in laboratories has been done for years, but doing this outside has been done for only 5 or 6 years. And the reason is that, as I said, these modules, they are in operation, they produce electricity, and as Torbjörn mentioned, when an electron acquires sunlight, it gets energized, and then it gets enough energy to leave the solar cell. It goes into the cable, to the grid, to your home, and it can power your electrical equipment. That is an oversimplified way to put it, but it's an okay image. What we need for our images is that once you have energized the electron with the sunlight, we don't want it to leave the cell and go into the cable. We want it to stay in it and de-energize. When it de-energizes, it emits light, which we capture, as Torbjörn explained. So we need to stop the electricity production in order to get these images. We need to make a way to say, okay, electron, you have been energized now, but don't leave, stay here. We need an image, and then you can go and become electrical current, basically. And that is not something that an operator would want us to do, to stop the production, obviously. And the research is now in a state, in the beginning state actually. We're trying to figure out the best way, I don't know if you can say that in English, to have our cake and to eat it, to produce the electricity and to get our images without stopping the electricity production too much. We need to find out what kind of electrical device we can use to somehow stop the production, but at the same time to do it in as short amount of time as possible. And we came up with a good idea last year, and we are now developing that idea, writing an article about that. And we hope that that idea would be a good step towards this type of imaging being used in the industry. So to sum up, we are trying to develop a method for imaging of solar modules. And we're trying to learn to interpret the images so that this method can be used in power plants, PV power plants, for the surveillance and monitoring of modules, in order for the operator to be able to find where the deficient modules are, change them out. Or what would be great is if we found out, okay, there's a deficient module here, but it still produces enough electricity so that we come up with the conclusion you don't need to change it out. So that is at the end the question of sustainability that we're trying to contribute to. That we have indications that we know that even this module that has been broken, it produces a lot of electricity on our site. So it could be possible that they don't need to be switched out, even though they have certain damages. Thank you.
Thank you so much. I think this is really cool. This side of the sustainability of like, how do we keep these devices running longer and more effectively, and how do we keep them going? Is this something that's these kind of power plants in Norway at all, or is this elsewhere?
As far as I know, there are no such sites in Norway.
Okay.
This big. This one is in Qatar. Yeah.
Thanks. All right. So are there any questions from the audience? This is another really cool talk. Timo, of course.
Oh my God.
Yeah, sorry. So you mentioned that you want to mount such device on drone.
Mm-hmm.
So my question, how do you manage to keep your resolution at the cell level while dealing with the motion? And second is like, do you use like CNN to make you to explain then behind after to have the case like directly say, oh, this one is too late to classify good, bad, maybe not.
Thank you. Two very relevant questions. The first one about how to get a good enough resolution and take into account the drone motion. That is something that my supervisor would like to look into. We still haven't.
Is a cellular cell, a solar cell, standardized internationally, or is it the same every country? Or is it by country?
The solar cell.
Yeah, is it the one in Qatar is the same Norway than in Germany, or is it different?
I think it depends on the producer. I'm not quite sure if I'm wrong here. It's more or less the same. Okay. Yeah. Yes, but this with because yes, drone motion and a good enough resolution, that is something that would be the next step. We are still on the level of, for now, on the level of the tripod. Luckily, with the better camera than this one, this is an old one, but we still haven't been in motion with the camera, neither on a type of vehicle on the ground nor up in the air. And the convolutional neural networks. We would need to have, that was the original plan for my PhD, but I've spent 4 years trying to figure out how to stop the electron from leaving the solar cell. So we would need more data to be able to, yes. And maybe somebody else will work on that, or I'll get more funding. I don't know.
That does sound like a common grad school problem. Any more questions from the audience? No? All right. Well, let's have another round of applause. And that closes out our speakers for the day, for the evening. If anyone would like to say a few closing words?
Thank you. Thank you. So thank you for being here today. We will, sorry. So the Pint of Science Festival is just started. We will have 2 other days. So we hope to see you again tomorrow, always at 6. Tomorrow we will be in another location. Please check the website and the social media. We'll find all the information with the program. Tomorrow will be the Green Day, so let's check it out. And see you tomorrow. Thank you again. Bye.
Don't forget to take the stickers.
Yeah, take the stickers.